Last time we got into this really interesting idea of improper integrals. And when we're talking about improper integrals, it's a different type of integral, which wouldn't be too surprising because we're already seeing two different types. We've seen the indefinite and we saw the definite type. Here's your third type, the improper integral. And as you keep going in your studies, you get to Calculus 3, you're going to see some other different types of integrals out there as well. They all work pretty much the same way. It's just little differences here and there you have to watch out for. The differences you got to watch out when looking at improper integrals is, first, you're integrating over an infinite region. So the region is going to be an unbounded region. And you can be unbounded to the right. You can be unbounded on the left. And you can also have a two-sided, so you're unbounded left and right. Now, for these up here, the definition is a limit. So the way that you work it is you would stop the clock, assess what's happening with the function, then take the limit. This part, this will equal only if both of these converge. If one of them diverges, guys, it's game over. It's not going to work. So only if they both converge, then you can add them up. When you see these types of integrals, you can break it up however you want. You can break it up at 0, you can break it up at 10, you can break it up at 100. It doesn't matter. Break it up however you want. As you go about it, I suggest maybe using some strategy just to make the problem a little bit easier. As we saw last time when we looked at the arctangent. Now, I must warn you again, if one of these diverges, the whole entire thing diverges. It's a little different type of integral. And what you have to be on the watch out for is it looks like it's a definite integral, but it's definitely not a definite integral. As you go about your integration, if I looked at, again, from negative infinity to positive infinity, if I had dx, x squared plus 1, it would be incorrect to say this for lots of different reasons. Okay. So avoid doing this, not correct. And another answer or another response that comes up from time to time is sometimes students will take a double-sided and what they're going to do is take it and recalibrate it. And they're going to say a goes off towards positive infinity, so I'll say negative a to a. And lots of times you'll see this in this example where you have negative infinity to positive infinity, you have x, you would have dx. Then they'll say, okay, well, let's just stop the clock, go ahead and integrate. A goes off towards positive infinity. Now they're x squared over 2 after they apply the fundamental theorem of calculus. They'll take everything, they'll plug it in, and they're going to get 0. And they say the answer is 0. But what we have here is a different type of integral, so you got to work it a little differently. If one of these pieces diverge, it's pretty much game over. What we would have here is we actually would have divergence. Why would we have divergence? Take your improper integral, split it up, and then send a off to positive infinity now. You get 0. No. So I got to be a little bit careful here as we're going through these types of problems. And let me just throw you another one that's really interesting. If a goes off to positive infinity, it would also make sense to say that 2a is also going to go off towards positive infinity. If I can take this and break it up, big if here, then could I not also take it and do the same thing? And again, it's a big if, where instead of going towards negative a, maybe go to negative 2a. Because if a goes off towards positive infinity, 2a is also going to go off towards positive infinity, and negative 2a is also going to go off towards negative infinity. But if I do this, there's going to be some problems which are going to arise really, really quickly. First off, if I looked at the integral, 2x, x squared plus 1, now I just simply integrate, we'll have the natural log x squared plus 1. Take the derivative, see if it works. Take the argument, put in the denominator, and then the derivative of the argument is going to be 2x. Okay, so that works out. And if we went from negative a to a in the first one, you would have the natural log, drop in your a, subtract it off, drop in the negative a. This part is going to collapse down to nothing. We get 0. And as a goes off towards positive infinity, we get 0. Do the same thing on this one now. And as a goes off towards positive infinity, what's happening to your argument? It's getting closer and closer to a quarter. And use the continuity of the logarithm, you get that. So which one's the right answer? Neither one of them. Because I'm working it in a way that I should not be working it. When I'm looking at improper integrals, double-sided, I can't work it like this. This is a different type of integral. And when you see this online, people are telling you to do this, they're talking about something called a Cauchy value principle theorem. It's completely different from what we're doing. We're talking about ordinary improper integrals. So don't do this, guys. If you want to see what's going to happen with these improper integrals, these type 1, what you're going to do is just check to see what's happening on the left, what's happening on the right, and take it and break it apart like we did right here. If one piece diverges, game over. Don't keep looking for something you already found. You found it, move on to the next problem. So the other thing that can make an integral improper is, what if you break continuity? You remember what it means for a function to be continuous? You can talk about holes in the graph. You can talk about jump discontinuities. You can talk about discontinuities at infinity. If I looked at f of x, 1 over x, this would be discontinuous because right whenever x equals 0, we're going to have that vertical asymptote. Here's the question. The whole entire idea of integration is this. Small parts form the larger picture. But what if the theory you're working with has holes and it has gaps in it? Would the small parts form the larger picture? Maybe yes, maybe no. At first glance, this looks like a definite integral, doesn't it? You have your endpoints, you got your function, it looks like it. But guys, it's not. Because at this endpoint right here, we're going to have a point of discontinuity. And whenever I have a point of discontinuity, I got to be a little bit more careful, more attentive to the problem. And I do not want to plug in 0, because if I divide by 0, the universe is going to explode. You don't want that. So what I want to do is get a little bit away from 0. As I'm looking at the graph, the 1 over x, I want to get maybe a little bit closer, maybe a little bit closer, a little bit closer, and just kind of test the water and see what happens. I just don't want to fall over when I get to 0. Well, that again is conjuring up this whole entire idea of a limit. So I can take this integral and I can express it in terms of a limit. And looking at the region from 0 to 1. And I'm coming in from this direction because my x values, as the endpoints suggest, are between 0 and 1. What I'm going to have here is I'm going to have a right-hand limit. So pretty much it works real similar to what we did for what's called a type 1, looking at an unbounded region for improper integrals. I'm going to write in terms of a limit. Then I'm going to stop the clock. I'm going to assess and see what happens. Then I'm going to take the clock. I'm going to run it up again. If I take the antiderivative or get the natural log, we'll do our evaluation. And in this part, we do apply the fundamental theorem on this part right here because there are no issues of discontinuity. We took the discontinuity and we popped it off. The natural log of 1, 0. So I'll pull out the negative, just make it a little bit easier to see. And we have this. So I have to go back to that skill set we developed back in Calculus 1 on limits and how to know if something's going to be converging or diverging. I suggest maybe just going back and looking at the graph, looking at the function, gives you a good visual as to what's about to happen. As a approaches 0 from the right-hand side, start coming in this way, well, your values are going down that way. This thing's dropping like a rock. This is actually going to be diverging. Okay. So at first glance, it really seems like it's a definite integral, but it's definitely not a definite integral. And what we have to do from now on is be very, very attentive. And it looks like it, but it's not it. It's very similar to someone who looks like they're family, but they're really not family in the end. Well, the first thing that I need to do when I'm looking at an improper integral from this time forth is really ask myself, is this a definite type or is this a improper type? It's up for me to decide from this time forth as to which procedure I need to go. And if I use the wrong procedure, the bridge could come collapsing down. Well, I need to identify if there's any points of discontinuity on the endpoints. So if I was simply just going to take 0 and plug it into my my integrand, would I get any kind of domain violation? No, not here. But I do have a domain violation right there. So this is an issue. And whenever you come up with an issue, you have a point discontinuity, take your point discontinuity, pull it off, and write in terms of a limit. So in general, if you're looking at an integral and you find that right here is a point of discontinuity, take it, pop it off, and you're going to be looking at a left-hand limit because you're coming in from the left-hand side. Assess what happens here next. Stop the clock. Find the antiderivative. Rinse, lather, repeat. All right, so for this one, we do, once again, identify discontinuity. Take the continuity, pop it off. You're coming in from the left-hand side. Now, again, it might be confusing to remember if it's left or if it's right. My suggestion is just write a number line. Put out your numbers. Where's your discontinuity? It's right there. And to get there, you go that way. So it's going to be a left-hand side limit. Left-hand of 1. How am I going to integrate this? Well, I can do a trigonometric substitution on it. I do see a difference of squares. And I might need to do that if I forgot that this integral really is arcsine. And let me ask you this question. What is the arcsine of 0? Remember that secret we talked about the other day? Inverse trigonometric functions are nothing more than angles. So what you're really asking is this. For what value of theta do I need for sine of theta 3, 0? It's going to have to be 0. To assess what happens here, I could go back and remember what the arcsine, what the graph looks like, and that's okay. But we can just simply look at what happens here with the sine graph. And just note that in order to talk about the inverse sine, the arcsine, we do have restrictions between pi over 2 and negative pi over 2. So I'm really just looking at that piece there. As b gets closer and closer to 1 on the left, what was the input that I needed? As I get higher and higher and higher and higher up, what was that x value? Pi over 2. And there it is. So here's a case in which the integral, yes, I do have a point discontinuity, but it does converge. That discontinuity is not going to cause any issues. Okay, first thing is, I spied my little eyes. Big, big problem. Point discontinuity. Once again, if I take that point and if I was just to plug it into my function, my integrand, I'm dividing by 0, and I don't want that. Okay, so when I see a point discontinuity, take the point discontinuity off the endpoint and write as a limit. Now, to be more accurate, we want to maybe look at from -1 to 0, looking at the region, because that is the region of integration. You are coming in from the right-hand side, so write in terms of a right-hand limit. It wouldn't make much sense coming in from the other direction because everything's not defined. Otherwise, you have complex numbers. And we don't want to talk about complex integration. That's pretty complex. Well, do the same thing. Go ahead and integrate. What's my output? My output, if I'm looking at the sine graph, is it's getting closer and closer to this thing called -1. And as I get closer and closer to the output of -1, what was the x value I needed? -pi over 2. But I already have a negative here, so I get pi over 2 in the end. So when I look at it from the other direction, from -1 to 0, it still converged. It's amazing. So again, if you find a point discontinuity, what you're going to have to do is take the point off, express it in terms of a one side of the limit, and see where the chips lie. What if I gave you this problem? Something that parallels what we did yesterday with a double-sided improper integral in an unbounded region. Here, I have an improper integral because I do have points of discontinuity. But it's just not one point discontinuity. Now I have 2 points of discontinuities. And one point is -1, and the other point is going to be +1. So what do I do in these situations? Very similar to what we did yesterday. Take your integral and break this thing up. Break it up however you like between -1 and 1. You can break it up from -1, you can go to 1/2. It's your choice, your problem, do as you please. Now you have 1 point discontinuity at -1 and 1. You would then take this and you would write in terms of a limit, and then you would apply the fundamental theorem of calculus on the inside part. In other words, you would take this, write as a limit, and then you would see what happens right there. And if this piece converges, and if this piece converges, then this right here will converge to the sum of those two values. If one of them diverges, it's game over. It's not going to work. You can break it up however you like. But since we know, once again, this is leading us to the arc sine, I probably want to use some value that's going to make this problem a whole lot easier. I want to set myself up for success. I don't want to set myself up for failure. I want to make it easier, so why not use what we already have? You can break it up at 0 if you want. We get pi in the end. All right, so if I have a 1 point discontinuity, not an issue. 2 points discontinuity, not much of an issue either now. Take it and just break it up like such. Okay, questions? Well, you can say infinity, that would definitely mean it diverges. You can say negative infinity, that would also diverge. But there's also one other type of divergence as well. What's the other type of divergence? So what? Not a whole. Anything that doesn't converge is to diverge. And to converge means you're getting closer and closer to some particular value. Okay, so if I look at this one, it's improper. I can assess it, stop the clock, integrate, negative cosine, 0 to b, plug things in, do a fast little shuffle. What's that limit? Well, let's maybe take that out. Let's do it like this. What's the limit for cosine? Does it ever get to one particular value? No. The graph for cosine starts up top and it does this. When does it stop? Does it stop yet? No. Does it keep going? Absolutely. Yeah, I better stop before I get to the end, right? So as this thing's going towards positive infinity, sometimes you're here, sometimes you're there, and back down again. So it is a type of divergence known as oscillation. Back and forth, back and forth. It's like a game of ping pong, back and forth, back and forth. And it's always going to be someone's turn. You're never going to hit the floor. It's always going to be up and down, up and down. Infinite game of Pong. There you go. So what if I had this integral? Well, when you look at it, do you have a point discontinuity at -1? No. Do you have a point discontinuity at 1? No. But this thing's sneaky. There's actually a point discontinuity again. It's discontinuous right whenever x equals 0. And that's smack dab right in the middle between -1 and 1. So whatever am I going to do in this situation? Take the integral, break it up at the discontinuity. So look at from -1 to 0, then from 0 to 1. Then assess to see what happens. And if one of these pieces, if it diverges, game over, you're done. Don't keep looking for something you already found. Don't look at the other one, you don't need to. Just look at one of them. Now, this definitely adds a layer of complexity to it. Because doesn't this really look like a definite integral now? I don't see any points of discontinuity on the endpoints, and it looks definite. But it's not. So you have to be very attentive. This thing is exploding, so this diverges. And you're done. Now, let me throw you this one. Let's say if I gave you this integral, and the question is this: does it converge or does it diverge? If it converges, why? If it diverges, why? What's your reasoning behind it? First off, do we have any points of discontinuity? Yes, there is a point of discontinuity. It's over here at 0. But where am I looking at? Between 1 and 5. Within this region, we can go ahead and just use the fundamental theorem of calculus. It's not going to be an improper integral on this region. If I also include this, then it's a different ballgame. This will converge. Why would it converge? There's no points discontinuity, so it is going to be a quote-unquote proper integral. It's not going to be an improper integral. If you can apply the fundamental theorem of calculus to it, yeah, guys, it converges naturally. or get some kind of response out of it. Hopefully, if not, you can maybe do some kind of a numerical approach to it. What happens here? What's the integration of tangent? Okay. Minus 1. What's the secant at 0? 1. What's my answer? It's not this. What? What do you mean it's not that? The integration of tangent is the natural log of secant. And secant at pi is going to be -1 because cosine at pi is -1. And the secant at 0 is 1. What do you mean that's not right? What did I do here? I applied the fundamental theorem of calculus to an improper integral. What do you mean it's improper? There's a point of discontinuity on the interior, not the exterior. So I gotta be really, really careful. It's sneaky. What happens at pi over 2? The whole entire house of cards collapses. So integration again, the idea is small parts form the larger picture. But what if you have holes and gaps in your theory? Will the small parts guarantee you're going to form the larger picture? No, it doesn't guarantee that at all. So you got to be real careful when things are discontinuous. Well, what I should do is take this and break it up. And break it up at the point of discontinuity and get to the end game a whole lot faster. In other words, I want to see the light of day. I want to take it and pull it up so I can really see the discontinuity. I would write it now in terms of a limit as b goes off towards pi over 2. And I'm approaching it from left side. Natural log secant. Plug in 0 to b. What's secant at 0? 1. What's the natural log at 1? 0. So this whole entire thing now collapses down to the natural log absolute value of secant. How am I ever going to figure out what happens here? Well, here's what I can do. We can come back and look at the graph. And I might want to look at not just one graph, but maybe want to look at 2 graphs. Here I'd have my secant graph. What does secant look like? Take your cosine graph, flip it inside out, look at the reciprocal. Where cosine crosses the x-axis, when you take it and you flip it and make the secant, it corresponds to a vertical asymptote. Okay, so there's the graph for secant. Just erase cosine and you got it. What does a graph of the logarithm look like? Something like that? So look what happens as b goes off towards pi over 2. As it goes off towards pi over 2, which is right there, so approach it from this direction, what's happening to my output arguments? Up and up and up and up and up and up. To infinity and beyond. It's going way up there. Well, these output arguments are the input arguments over here. So this output is that input. That output is that input. That output, so on and so forth. So as we're growing up on the secant, all these values are coming over here. And what's happening to the logarithm graph now? That's exploding. It's going towards positive infinity. So sometimes I might have to look at, when we're looking at compositions, not just one graph, I might need to look at 2 graphs to really see what's happening. It's possible that this could go off towards positive infinity, but when I plug into another function, it's possible that it could actually converge, like when I have 1 over x squared plus 1. All right, so what happens here is we have divergence. This thing's going to go towards positive infinity. All right. So here are 2 different types again. We have our type 1, we have our type 2. And the next question is, can you mix them together? Have a type 1 and a type 2? Well, you're going to have to come back next time and find out. Live in suspense. You guys have a great day.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.